Hi, hello everyone. I hope everyone is doing fine and staying safe. Really excited for today's talk with Rick with the researcher series. We will start by presenting our guest, then we will get into the presentation. While you guys can ask any questions that you have, you can leave them in the comments. And at the end, I will ask your questions to Jessica. So we are honored to have with us Jessica Hamrick. She's a senior research scientist at DeepMind. Her work combines insights from cognitive science with structured relational architectures, model-based deep reinforcement learning, and planning. And today's talks will be about structured computation and representation in deep reinforcement learning. So I have here Jessica.
Hi, thanks so much for inviting me to be here today. Okay, let me put up my slides. Are you able to see these? Okay. Great. Okay, I think, yeah, they're up. All right, perfect. So, so today I am going to be talking about some of the work that we've been doing at DeepMind to build various forms of structure into our deep RL agents. And I thought I would start by first actually just telling you a little bit about my background and say like how I ended up at DeepMind and how that's influenced my research trajectory, just to make it a little bit more personal and also kind of, I think, highlight like how having, I guess, like a background maybe that's not necessarily in machine learning specifically, might influence your whole research trajectory, as it is the case for me. So I've actually been interested in AI for a long time, starting in high school when I was on our high school robotics team. So FIRST Robotics is a program in the United States where high schoolers form teams, they build a robot, and then the robots have to compete in various games. After finishing high school, I went off to study computer science for undergrad and continued working on some robotic stuff, specifically on this robotic teddy bear called the Huggable. And I took a lot of classes on AI and related topics as part of my coursework, but over time, I got a little bit disillusioned with the current state of AI, at least as it was in the late 2000s, because it seemed to me to sort of ignore the best examples that we have of intelligent systems, which is humans. So I began looking around for sort of other options, and I found in the Brain and Cognitive Science department, Josh Tenenbaum's group, who was studying computational cognitive science. And there I began doing completely different research, looking at how humans reason about physical scenes like this tower of blocks and trying to model their behavior. And this sort of inspired me to continue research into humans rather than into AI specifically. So I went to do my PhD in psychology, working again in another computational cognitive science group led by Tom Griffiths. And during my PhD, I got sidetracked by some other things too. Like I spent a lot of time contributing to open source projects like Jupyter. I formed some collaborations with robotics researchers at Berkeley, which then reignited some of my interest in AI. And eventually I did an internship at DeepMind, which I enjoyed so much that I decided to come back here full time after finishing my PhD. So sort of, as I said, it's been a little bit of a non-standard trajectory for me. Rather than doing like the standard PhD in machine learning, I did it in this related field of computational cognitive science. But I think that's actually been really valuable for me and has provided me a bit of a unique perspective on how to approach problems in AI. And so I think maybe some of that will come through today as I give this talk. So one of the things that I spent a lot of time thinking about during my research into humans is how people conceive of the world in terms of objects and the interactions between those objects. So for example, we understand what's going on in this scene is not just about what the people are doing, but that they're doing exactly the same thing together at the same time. They're coordinated. Now, we also understand this image in terms of the animal that it depicts, of course, but we also understand that there's like a hierarchy of objects here, right? From the deer to the individual parts of the deer, like its antlers, and even the broader context in which it's embedded, which is the scene. And we understand the rules for composing objects, allowing us to build them into more complex structures and scenes that are greater than the sum of their parts, like stacking blocks into a tower that's stable. So understanding the world in terms of objects and relations is another way of saying that we understand the world in terms of structure, which is defined as being the arrangement of and relations between the parts or elements of something complex. We as humans are biased towards assuming that things in the world decompose into other things, and that there are reasonably systematic rules governing that process. This bias towards structure has, of course, been programmed in over the course of evolution, enabling humans to quickly learn from small amounts of data and to perform well in a vast and diverse range of situations. And so I think that we can gain similar benefits in machine learning by thinking carefully about the type of structure that we build into our models so that it acts as an appropriate inductive bias, prior, or regularizer over the space of possible behaviors. And there's lots of ways, of course, that we can build structure into our models, but I want to focus on sort of dividing the two types into two categories. One of structured computation, which is the way that the individual computations or functions are composed into more complex structures, and structured representations, which is the format of the data that computations are performed over, like sets, graphs, programs, or so on. So we can view, say, structured computation and structured representation in terms of existing components in deep learning. So, for example, one of the most commonly used ones is the fully connected layer, which you can sort of see as performing a type of unstructured computation and unstructured representation. The representation is unstructured because it just takes in a vector. There's no particular structure, and any part of that vector could correspond to anything, any value of information. And then the way that that vector or tensor is processed is by performing different computations at every element. So each element gets processed in a different way. There's no sort of sharing or anything. This changes, of course, in some of the other components that we commonly use, like convolutional layers. Here, they're still operating over the same types of representations, which are vectors or tensors, but we're starting to see a bit more of a type of structured computation here. For example, the convolutional kernel, is applied at every part in the input of the image, and that means that you have this sort of sharing of computation. Every part of the image is processed in the same way, so you have the sharing in space. And it's a similar story for recurrent layers too. Here you get a sharing in time. You have, again, something that's like, just a vector or a tensor as input. It might actually be a little bit more structured because you might have because it's a sequence and it might be, say, an unbounded sequence. You can unroll your recurrent layer as many times as you want. But it's still, still typically closer to an unstructured representation. But then you, again, apply the same computation at each point in time. So that is another form of structure in the computation. And of course, you can go even further than that. It's very common for deep learning practitioners to design sophisticated architectures by composing deep hierarchies consisting of various types of layers, like convolutions and fully connected layers, which lead to very highly structured forms of computation, like you can see in many of the vision architectures, like the inception architecture here. But in reinforcement learning, which is the area that I spend most of my time thinking about, the dominant paradigm is what we know as model-free reinforcement learning. And model-free reinforcement learning typically looks like this, where you have a state of the world. It's passed through some network that produces policy or estimates of value for the actions that you want to take. So basically says how good each action would be to take. And then you, from those set of values, you decide which action you actually want to select. But this is typically composed of mostly unstructured computation. So there's maybe like a few convolutions or something like that, but by and large, there's not very much structure there. And similarly, the states are also these unstructured representations like images and unstructured actions, meaning like you have a fixed size action space and you always have to select from those actions. So a good example of this is the DQN agent, which takes in, again, unstructured representations, which are images. It computes using a couple layers of convolutions and fully connected layers, and then outputs a fixed size action space according to what you can do with the Atari joystick. But I think if we take a step back and say, is this, how does this compare to, say, how humans reason about these types of scenes? Like, we clearly reason about them in a more structured way. We think about the objects on the screen. And we conceive of actions that are very goal-directed, like destroy the blue block first, or all of the blue blocks first, or maybe get the ball above and destroy the layer on the top. And we plan ahead in time. And that's not something that we see in these types of architectures here. So in this talk, I want to challenge this dominant paradigm and ask about ways that we can incorporate more types of structure into RL in order to reason more compositionally and achieve better generalization. So specifically, I'm going to talk about two projects that make particular assumptions about the structure of the computation and the structure of the representation in reinforcement learning settings. First, talking about ways to structure the representations inside the agent's policy and structuring the actions that it takes in the world. And second, ways of leveraging models of the world to produce more robust behavior with stronger generalization. So let's start off by talking about incorporating structure into our representations. This is work led by Victor and Alvaro, who are two of my colleagues at DeepMind. And in this project, we were interested in developing agents that were able to solve challenging compositional tasks like stacking blocks to achieve a goal. So to this end, we designed a series of tasks in which the agent sees a scene that looks like this, with a set of blue blocks below the floor here and some number of red obstacles above the floor. So the agent's job is to pick up the blocks and place them into the scene, avoiding the obstacles as it does so. And the agent can also choose to make the blocks sticky. So you can think of them as like being dipped in glue or something like that. And that'll cause them to stick to any other blocks or obstacles that they come in contact with. So in this domain, we developed several separate objectives for our agents to solve. In silhouette, the goal of the agent is to place blocks to match these green silhouettes. So here's an example solution of the task where you can see the blocks stacked on top of the silhouette. And some of them are teal, which indicates that they've been made sticky. And the gray dots between the blocks indicate where they're sticking together. So you can see these here. And then for each silhouette that the agent fills in, it gets 1 point. And it also pays 0.5 points for each block that it makes sticky. In the connecting task, the goal is to stack blocks to connect the floor to these targets in the sky. And this task is more challenging because the final structure is really underspecified. It requires the agent to really design a solution to get the blocks from one point to another point, rather than just filling in a structure that's already been given. And then in the most difficult task, covering, the agent's goal is to cover these obstacles from above. So you can sort of think of this as requiring the agent to build shelters from the rain. So if the obstacles are covered, then they should stay dry in the rain. I should also mention that these tasks are open sourced as of a few weeks ago. So if you think these environments are interesting and you might want to play around with them yourselves, I would encourage you to check out the open source release. Okay, so how should an agent interact with these sorts of environments? Well, a common choice of action space would be to have the agent take absolute action. So this would be sort of like the standard thing in the model-free paradigm. So you would say like, okay, I'm going to pick up this block, D, and place it at position 7.2, 8.5. But in talking about these sorts of environments, I would never say, if you asked me to describe what I was doing, I would never say like, oh, I'm about to place this block at position 7.2, 8.5. I would say something more along the lines of, I'm going to place block D on the top left of block B. And so to implement this type of action, we can have the agent directly choose which object it wants to move, which object it should place relatively to, and then an offset location of where it should actually place that object on top of the other. Intuitively, you can think of this as a little bit like placing a Lego brick. You need to pick up a Lego to choose which one to stack. You have to choose another Lego to put it on top of, and you have to choose the dimple where the top Lego should be placed. But it's not really obvious in the traditional model-free paradigm how to actually implement this type of action format in an RL agent, since in the standard paradigm that I talked about before, the input space and the action space are both fixed in size. But here, since we're defining actions based on the objects in the scene, we want to place an object on top of another object, the number of actions will change as the number of objects changes. So to deal with this problem, we designed a new type of agent that we call the GN-DQN agent, which operates over graphs. Specifically, here, say, is the input scene. So we have a set of objects and obstacles. And what we're going to do is we're going to treat the scene like a graph, where each object in the scene is a node in the graph. And these nodes have attributes assigned to them, such as their position, the size, so on and so forth. So we now have a graph structured observation, but we need a neural network to process this. And this is not really something that, again, the sort of traditional components will allow you to do. Neural networks that operate over graphs have been around for a while now, first pioneered by Gori, Scarcelli, and many others, and now they're quite popular, so perhaps you've heard of them already. But a few years ago, they weren't quite so popular yet. So my colleagues and I released a review of this literature and unified various approaches that existed at the time into an architecture that we call graph networks. And graph networks have a few important features, which are that they take graphs as input and they return graphs as output. So a graph is defined as being a set of nodes and edges and maybe some global properties as well. So you pass all of those things in, to the graph network, as you can see here in this diagram. And then it does some computation over those nodes and edges and global properties and outputs another graph, which has a different set of attributes for the edges, nodes, and globals. The graph network is invariant to the permutation of the nodes and edges, so it doesn't matter what order you pass in the nodes or what order you pass in the edges, it's always going to give you the same answer. And the reason for that is because it does a lot of local computations over the individual nodes and edges and doesn't process the graph necessarily as a whole. It does these individual computations. So you can think of it as sort of like convolutions, but generalized to the graphical setting. But perhaps the most relevant feature here, at least for our purposes currently, is that graph networks can scale to different numbers of nodes and edges. So they're not going to necessarily give the same answer if you've given a different size graph, but it'll still be able to process that. And that's, again, because it does these sort of local computations over the individual nodes and edges, and that allows them to just do more computation, if you need to, for graphs of different sizes. So coming back here to this picture that I showed you before, we have our graph representation of the scene. We can pass this into a graph network, and then this gives us out a new graph, which has activations on the nodes and edges. In this particular case, we care specifically about the edges of the graph because we're going to take those activations on the edges to correspond to the actions that we want to take. Specifically, if we have this edge here between block D and block B, we would treat this as placing block D on top of block B, and then the particular activation that we have, like the particular location of this activation, would correspond to the offset, so corresponding to its top left. And again, if it helps to understand this a bit better, just remember the Lego analogy. What we're basically doing is treating each one of these nodes as the two different Legos, and then the specific activation as the dimple where you want to place it. So we compared this graph network agent to several other agent architectures. I'm not going to really go through the details of them, but we tried to be pretty thorough in terms of comparing to like a fairly wide range of baselines here. But the important thing here is that these other types of architectures don't have the same notion of the structured representation and the structured actions that our full GN-DQN agent has. And we can look at what are the implications of this. So here on the top, what I'm going to first show you is the reward that's achieved on the hardest levels of these tasks. So we have different levels of difficulty. And so this is just looking at the hardest level. And we can compare these agents that use these absolute actions, like I mentioned. So just placing, say, an object at, position 7.2, 8.5, versus these relative actions, like place a block on top of another block. And across the board, what we find is that the best agent that uses these absolute actions really can't get off the ground very much and is really strongly outperformed by this agent that takes relative actions. And similarly, if we could just consider the structure of the policy itself, does it use a graph or not? Or does it use something like convolutions or recurrent layers instead? We find, again, that this graph network that explicitly knows how to deal with the structure of a graph is much, much better than the alternatives. I think the most compelling example, though, here is just to actually watch the videos. So here on the left, you can see an agent that uses the unstructured representations and unstructured actions compared to an agent on the right here, which is the GN-DQN agent, which uses these structured representations and structured actions. And so you can see that the unstructured agent really has a hard time solving this task. It can get usually a few blocks, but it can't normally solve most of them, whereas the structured agent is pretty much able to do this task flawlessly. Similarly, on the connecting task, where again the goal was to stack blocks to reach these points in the sky, you can see that these unstructured agents kind of fall into this degenerate strategy where they're just stacking blocks up on the edges of the scene and trying to reach them into the center to reach these target locations. And they haven't really learned about the structure of the scene in the sense that they can actually stack blocks in between these obstacles. But that's exactly what the structured agent is able to learn how to do. And so it's able to get all three targets on most of the scenes. Again, similarly with covering hard here with the unstructured agent, you see a similar pattern of behavior as with the connecting task. Again, it stacks the blocks up on the side and then tries to sort of curve them inward to cover the obstacles. which can work in some settings like this one here. But if the obstacles are too far apart, then it really is much harder for it to solve the task in that way. As opposed to the structured agent has learned a much cooler strategy, which is to sort of create these like tree-like structures and then compose those tree-like structures into things that look like arches. So we were really excited to see that. And finally, we also had another variant of the covering task, which is called the covering hard task, where we only allowed the agent to use exactly these blocks that were on the bottom, so rather than using all of the blocks, and we made the price for using sticky blocks much higher. And again, with the structured agent, you can see that it has sort of like one dominant strategy that it uses, which is to stack stuff up and like sort of curve it over to the left hand side here. And like you often see these really like long chains of things, whereas the behaviors produced by the structured agent are much more creative and interesting. Okay, finally, we looked at also how well these agents are able to generalize to new settings that they haven't seen before. So here are just like a few potential settings. So like in Silhouette, we always trained the agents on 8 blocks, but then we asked them to generalize to scenes that required them to place 9 or 16 blocks. And similarly, in connecting, we could change like are all the target locations that it has to reach during training. Those were always at the same level, but we can make them be at different levels, or we can make those targets be one layer up and have an additional layer of obstacles that it has to weave through. And again, we find if we use these like absolute actions, the unstructured form of the agent, it really isn't able to generalize that well, and its performance really suffers quite a lot. Whereas with these object-centric structured agents, the GN-DQN agent, we see really nice generalization performance. And you can see here actually that the performance in Silhouette, or the absolute reward, goes up, and that's because there's more objects to match. So a maximum reward would be probably closer to 16, so it's not completely generalizing perfectly, but it's doing a pretty good job. And you can see that here. So here's an example of generalizing to 16. Yeah, there we go. Here's an example of generalizing to 16 blocks, and you'll see at the end it doesn't quite get it. It sort of misses the last block, but it almost gets it. And this is really, really impressive zero-shot generalization, that it can almost solve scenes with twice as many objects as that it saw during training. So the key takeaway from this is that we can achieve this really impressive form of compositionality and combinatorial generalization by using representations that are structured in a way that reflects the structure of the environment itself. So let's go back to our outline now and move on to the next section of the talk, which is to focus less on the representations and more on the types of computations that we're performing. So specifically, consider the diagram I showed you earlier about the sort of dominant approach in model-free RL. So we already saw in the last section how using able to reason compositionally. But we can also think about ways that we can further structure the computation of the policy to get even more benefits. And one way that we can do this is by using a model-based approach, which incorporates more structure into the computation by factoring it into a model of the world, and then some search or optimization procedure that operates over that model of the world. Now, model-based RL is a really big topic, and there's been a lot of exciting work in this area recently. If you're interested in learning more about this, I wrote a review article a year ago that you can check out. Also, I just gave a tutorial with Igor Mordach at ICML, which is freely available online if you want to look at that as well. So model-based RL is a big topic, lots of exciting work. And one of the things about model-based RL is that there's a lot of choices about how a model specifically can be used. In other words, how does the search procedure work, and how do we use the result of the search procedure most effectively? So how do we structure that type of computation? So in this project, we began with a fairly standard search procedure, which is known as Monte-Carlo tree search, or MCTS. And we explored how we can leverage the structure in the agent to perform more efficient search and more effective learning. The result is this new algorithm called SAVE, or search with amortized value estimates. And the way that SAVE works is, so we're going to start with just model-free learning. So this is, again, just a different way of drawing the typical model-free setup. We have a Q function that produces actions. We send those actions to the world. We get some reward. Then we use the rewards. We perform Q learning with those rewards in order to update the Q function so that it can give us better actions. What we're going to do, the sort of departs from this, is to now incorporate this process of search. So we take our Q function and we use that to guide a process of search, which then produces updated Q values that we can then use to select our action. So specifically, what it means to guide the process of search looks as follows. So let me first just walk you through how MCTS works, and then I'll tell you how SAVE modifies this procedure. So in Monte-Carlo tree search, we have here our root node of the search tree. So that's the state that the agent is currently in. And we're going to initialize a set of Q values. So that's, again, estimates of how good the actions are that it can take, as well as visit count. So how frequently has it visited each state in each action. Then we expand nodes according to a search policy, which is basically the Q values. So again, how good each action is, plus some exploration term. And so whichever action has the highest value here, we'll select to expand in the tree. And we'll do this until we reach a new node, like this one here, that hasn't been visited before. And then we're going to estimate its value using something like a Monte-Carlo rollout or maybe a value function. Then we perform a backup. So for all of the parent nodes, we update the Q values as just being the empirical mean of all of the traces that have passed through that, that node before. And we update our visit counts, so that makes this computing this empirical average in the future easier. And then we repeat this until our search budget is exhausted. So again, we expand until we reach a new node that we haven't seen before. We then evaluate it, and then we back up its value, and so on and so forth until our search budget is exhausted. So MCTS, as it works like this, what you'll notice is that it basically starts from scratch. So it doesn't know anything about like which actions are best to take at the very beginning. All of these Q values are initialized to 0. But what we can do is we can guide MCTS using a prior, for example, our prior Q function, and then allow that to guide the search in terms of this expansion policy. So what we'll do is we'll take our Q function that's output by the neural network, and we'll set our Q values to be equal to those Q, to that Q function. And so that means that when it starts expanding nodes in the search tree, it already has some idea of which actions may be better to explore and visit than others. So that's what it means for the Q values to guide search. And now there's a third component here that is very important, which is that we basically amortize the computation of these Q values back into the model-free Q function. So if we don't do that, we could just say, like, okay, we're going to allow the Q values to guide search, produce new Q values, and then select our action from that. So basically just use the search as a way to select better actions for the agent. But in addition to doing that, we're going to use this computation of the search itself and sort of force the prior, this Q value prior, to look more like that. So we're basically able to reuse the computation more effectively. And the result of doing this is quite striking. So let's come back to our construction tasks that I talked to you about. So here I'll show results on connecting, covering, and covering hard. And what you will be able to see here is that SAVE really strongly outperforms not just model-free, but also something which doesn't do this amortization of the computation. So here in green, you can see SAVE, and in blue is the model-free agent, and pink is an agent which uses the search, but only to select action. So it doesn't have this amortization loss in it as well. And on the x-axis, you can see different amounts of search being used at test time, and on the y-axis is the reward that's achieved. And the model-free agent and SAVE, all of these architectures are using the same GraphNet-based architecture that I talked about earlier. So this is already starting from very, very strong performance. And so again, while the model-free agent is doing quite well, as we saw in the previous section of the talk, once we add in search, and in particular, once we add in this amortization loss, we can see even better performance in all three tasks really reliably and robustly. If we also look similarly at our generalization results that I showed you before, this is what I was showing you previously. And again, if we add search on top of this, then we get even stronger generalization performance. So here in the silhouette task, where before it was able to almost generalize perfectly, but not quite, now it generalizes perfectly almost all of the time. So it's almost perfect generalization, which is really nice. We can try to look at how SAVE performs in more complex environments as well. So we developed a new type of construction task, which we call Marble Run, which the goal is to stack up blocks in order to support this ball getting from this location to this target location. And and again, the ball is not allowed to touch any of the obstacles like these ones here or the walls. So again, here we find SAVE is really able to do a much better job than, say, your standard model-free baseline. As you can see across all of these different levels of difficulty that we trained it on, it's basically at ceiling performance at the easier levels. Of course, it's still not doing quite so great at the harder levels of difficulty, so there's some room for improvement, but it's still substantially better than the alternative. And here you can, again, see a little video showing the agent successfully able to stack the blocks to get this ball from its initial location to the target location. Okay, and I guess just to show that this works not just in these sort of like our handcrafted like construction environments, we also tried to test SAVE in more sort of well-tread environments like Atari. So we took a powerful model-free baseline, which is known as R2D2, and we added SAVE on top of it. So we basically took R2D2, which does Q-learning, and then added search and this amortization loss on top of that. And we find that SAVE outperforms the baseline version of R2D2 in pretty much all of the games that we tried. So the key takeaway here is that we're able to leverage additional structure in the computation by combining model-free priors with search. Which then produces more robust behavior and better generalization than if we just had a model-free agent, or even if we just used search alone. It's this idea of thinking about the computation of the search and figuring out how we can best use that and reuse that that really leads to this strong performance. So just as a recap, in the talk, we talked about both structured representations, like using GraphNet policies in order to solve these construction tasks, and structured computations, like leveraging search. And just to summarize, I think that building agents which are flexible, adaptive, able to generalize is really about building the right structure into their architectures, like model-based computation and representing the world in terms of objects. And ultimately, I think that this involves thinking both about the general structure of the computation needed to solve the problem, as well as the structure of the underlying representations and actions that are actually taken in the world. So I just would like to thank all of my collaborators and co-authors on all of these papers. Here are the references again, if you're curious, as well as the link to the construction tasks. And thanks for listening and for inviting me here. And I'm happy to answer any questions. Thanks a lot.
Thank you very much for this presentation. It was really helpful and definitely interesting. For questions, we have a couple of questions. Concerning the graph networks that you have already mentioned, like how did the idea come to you, and are you still working on it to improve it even more?
Yeah, great question. So graph networks have been, I guess, something that was like, so me and Pete, who is my collaborator here at DeepMind, who I've worked on a lot of this stuff with, like we have been thinking about these sort of ideas from cog-sci for a long time in terms of like the world is composed of objects and their interactions, and so we sort of came from it from that perspective. So we were thinking about like I mentioned like earlier in my career I worked on this stuff like stacking tower, like having towers of blocks and reasoning, say like how does the tower fall or what direction does it fall in, and that involves a process of reasoning forward physical dynamics. So how can you get an agent to learn physical dynamics? Well, the structure of a physics engine is really like you take each of the objects and then they have some velocity, and so you say, okay, well, their next state would be, if I were just to project them forward in time, would be this, but then you have to resolve the collisions. The collisions are now interactions between things. And so this sort of idea of thinking about like these types of objects and relations then naturally sort of translates into this graph structured representation. And as I mentioned, like, we didn't invent graph networks, but when we sort of like realized the relationship between like what we were thinking about in terms of this intuitive physical reasoning and these like existing graph network or graph neural network structures, and seeing the relationship between those, and then seeing like, can we sort of push that forward? And I'm not really working on this line of work so much anymore. So I'm more on looking at like planning sorts of things. Like the second project that I talked about with SAVE is sort of what I've been focused on most recently. But I expect at some point I will probably come back to thinking about, again, like the structured representation side of things, because I really feel like these are two sides of the same coin, and it's important to think about both of them. And so I won't stay away for too long, I think.
Okay, so you are still working also on the SAVE project. You are still.
Yeah, well, thinking about in general, like questions surrounding planning, and like when does planning work well, and like what sorts of like planning algorithms can we develop that work even better than the ones that we already have. And so, I mean, I didn't really have time to get into this talk, but I think, again, like there's a lot that we can look at by paying attention to human cognition in terms of how humans use their models of the world, and we run mental simulations, so we can imagine all sorts of things. And there's that basically is like a form of planning. And there's so much in terms of how we use our models of the world and how we engage with planning that we don't really see in model-based methods currently. And so I think that there's really a lot of room to continue innovating in that regard.
All right, thank you for answering that. Yeah, another question is concerning, you mentioned in the beginning that there are some networks that are using structured computation but not structured representations. So if you use the SAVE method on those networks, will it perform better? Will it give us better results?
Yeah, so actually that's exactly like, I didn't show the slide for very long, but let me show this again. Oh, I guess maybe.
Yeah. Okay.
Yeah.
Sorry.
Yeah. So here are these results I was showing on Atari. So I mentioned that this is just adding SAVE on top of the R2D2 agent, and the R2D2 agent is really like a very sort of like typical model-free agent. It takes in images and it processes them using like some convolutional layers and some MLPs, and then produces a flat action. And so this sort of experiment is an example of using a more structured form of computation, but with a unstructured representation. And so yes, they definitely can work better to do this as well.
And we can use the structured representations over these too?
Yes, well, that's a little bit more of a challenging question, or challenging answer, or complicated answer, I guess I should say. So what we did in the construction task is we basically assumed we knew already, like, what are the objects in the scene. And that is, if like all you have are sensory data coming in, from like a camera or whatever, then you don't have that information. So if you wanted to use a structured form of representation in that sort of setting, you would have to go from you still have to start somehow from an unstructured representation and map it to a structured representation. But there's a lot of work on this currently. I actually was a co-organizer for a workshop at ICML called the Workshop on Object-Oriented Learning. And there was like, you could see like basically the latest and greatest methods for how to basically pull out these structured representations from unstructured data in an unsupervised way. So there's a lot of interest in that and a lot of exciting work going on in that right now. But that is the sort of like the way of going for like the perception part is a little bit less my area of expertise. So I'm focusing more on the part, like once you already have the structured representation, like what can you do with it? But it's an important piece of the puzzle is how do you solve that perception part too.
Okay, thank you very much for your answer. Now there's a question about if you could give us brief about your experience with DeepMind.
Sure. Working at DeepMind is great. I'm not sure, I guess, like what part on it you want me to comment on, but I would say like it really feels a lot like being in academia in a lot of ways. Like I didn't really feel like when I left I went directly from grad school to DeepMind, and it didn't really feel like I was coming to work for a company. It felt like I was coming to work for a research lab. Like just, it's structured a little bit differently, but by and large, like my day-to-day is pretty much the same. I read papers, I write code, I write papers, I give talks, and it's really a great environment because there's like so many people with so many different backgrounds and areas of expertise that like if I'm interested in some aspect of machine learning that I don't know very much about, I can find someone who is and talk to them and say, oh, I think like maybe this thing would be useful for my project. Like, what do you think? And then it's really easy to sort of like form collaborations and get involved with people in that way. So I really it's a really great place to be as a researcher.
Okay, thank you. One last question is that your recommendation for people who are just starting with AI and wants to go to reinforcement learning and with the good courses and books and resources in general.
Yeah. So I would say start with what interests you. Like, so if there's like a paper you think is really interesting, or like you see a talk and you think the methods that they talk about in that paper are really interesting, go and try to understand those things. Like follow what is interesting to you, because that is like what's going to let you have the most motivation and excitement to like keep working and understand it. And then I would say like working with stuff hands-on is really, really helpful, like actually going in and trying to re-implement the methods that you see. I mean, maybe if you're going to try to implement something, don't start with the most like complex things. So see if you can like boil it down into something more simple. So like, for example, if you wanted to like say, if you were interested in like the graph network agent that I showed, I wouldn't start with that because it's a really complicated agent, but you could say like, start by implementing just a very simple version of the DQN agent. And then there's things like, OpenAI Gym and all these things have a lot of examples for how to implement these types of agents and train them on simple versions of tasks that you could even potentially, in some cases you can like train them on your laptop. And I think in terms of like courses, if you sort of just want like a more general overview, I would like David Silver's course at UCL is really good for reinforcement learning. I'm not sure I have what the best recommendation is that I would have for deep learning, since I didn't actually really take any courses on deep learning myself. But I did find Nando de Freitas has a really good course online that's sort of more general machine learning, but the course was given sort of before the deep learning era. So it kind of has the foundations of machine learning, but not specifically the deep learning components. But I would probably expect that any of these like big, sort of online courses on deep learning are probably a pretty good place to start too with that. So.
Okay. So yeah, thank you very much also for the answers and for the presentations. The questions are done. Okay. We were honored to have you here with us today, and it was a very interesting talk. So thank you very much for accepting the invitation too.
Yeah, thank you so much for having me here. I hope it was interesting and useful. So.
Yeah, thank you.
Thanks. Bye.
Bye.